A 5 kilo block is dragged along an inclined plane with an incline of 30 degrees, a static friction coefficient and a kinetic friction coefficient, and released with an initial speed of 5 meters per second. Calculate the maximum distance travelled by the block up the plane. So we're looking for this distance over here. So taking our reference point at A, we have the kinetic energy of the block at A, plus the potential energy at A, minus the work done by the kinetic friction force, is equal to the kinetic energy at B, plus the gravitational potential energy at B. So therefore, we have 1/2 by the mass of the block by the square of the speed, and the potential energy at our reference point is 0, and minus the work done by the friction force, which is the kinetic friction coefficient, by the mass of the block, by the gravitational acceleration, by the cosine of theta, which is 30 degrees. So remember, the kinetic friction force was obtained by a force equilibrium in the direction perpendicular to the plane. And the work done by the friction force is the friction force by the distance d. And that's equal to the kinetic energy at B, which is 0 because we want to find the maximum distance, so the block comes to a stop, plus the potential energy at B, which is the mass of the block by the gravitational acceleration by the height. So this distance is d sine theta. And calculating this out, we get a distance of 1.48 meters. So the correct answer is B. A block with a mass m is dragged from rest up a plane to a distance d under a constant force, and then the block is then released, and we're asked for the speed of the block when it travels a distance of d on 3 down the plane, and we're given a kinetic friction coefficient. So if we do a conservation of energy between points A and B and identify the forces acting on the block, so we have the force of weight, the kinetic friction force, and the normal force, where the normal force is always perpendicular to the motion or the displacement vector, so it does no work. And now we can do a conservation of energy between A and B. So the force does work over a distance of d, minus the work done by the kinetic friction force. So recall the kinetic friction force was obtained by using Newton's first law in the direction perpendicular to the plane. So that was mu k by mg cosine theta, and the friction force does negative work over a distance of d plus d on 3. And that's equal to the kinetic energy at B, which is 1/2 by m by the square of the speed at B, plus the gravitational potential energy, so that's mg by 2d on 3 sine theta. And now we can solve for the speed at B. So multiplying through by 2 and dividing through by m, we get 2fd on m minus 8 on 3 by mu k by gd cosine theta. And we take the potential energy term to the left hand side of the equation. So we have minus 4 on 3 by gd sine theta. And then we take the square root, and that gives the speed at b. So the correct answer is C. Given the potential energy diagram below for a harmonic oscillator, which has a mass m attached to a spring with a stiffness k, where the mass is released from a distance of x naught from the equilibrium position, write the equation for the speed of the block in terms of the mass, spring stiffness, x naught, and x, where x is some distance from the equilibrium position. So we have the energy input into this system being equal to the potential energy at x naught, being the position where the mass is released from, and that's equal to the kinetic energy of the mass plus the elastic potential energy stored in the spring at some distance x. So the elastic potential energy at x naught is 1/2 by k by x naught squared, which is equal to the kinetic energy plus the elastic potential energy at x. And multiplying through by 2 and dividing through by m, we obtain k on m by x naught squared, and subtracting this term from the right hand side, we get minus x squared, and taking the square root gives us the speed of the block. And note that this system is bound such that x is between minus x naught and x naught. Otherwise you'll have energy coming out of nowhere, so the mass oscillates back and forth between these two positions unless an external agent inputs energy into the system. So given we're asked for the speed, the correct answer is C. Given a potential energy diagram below for a harmonic oscillator, which has a mass m attached to a spring with a stiffness k, and the mass is released from the position x naught, being the distance from the equilibrium position, determine the maximum speed, and state if this bound system has a stable or unstable equilibrium point. Well, the maximum speed occurs where the potential energy is at a minimum, which is at the equilibrium point. So the energy input into the system, being the elastic potential energy at x naught, is converted into the kinetic energy of the mass. So if we solve this equation for the speed of the block, we get x naught by root k on m. And recall that a conservative force is equal to the negative of the derivative of the potential energy function with respect to x, and the equilibrium point occurs where the force in the spring is 0. So remember that the force in the spring has a magnitude of kx, so the equilibrium position is at x equals 0. Now to the left of this equilibrium point, the slope of the potential energy function is negative, so negative and negative gives positive, and the force in the spring points towards the equilibrium point to the right. And to the right hand side, we have a positive slope of the potential energy function, so the force points in a negative direction in this case. So this is a restoring force that restores the system to the equilibrium position. So that's a point of stable equilibrium. And the correct answer is D. If a ball with a mass m is thrown vertically upwards at an initial velocity v0 and reaches a maximum height h, determine the average power of the gravitational force when the ball reaches h on 2. We'll recall that an average quantity, using the mean value theorem, so here we have the average power, is equal to 1 on a change in time by the integral of the instantaneous power over time. And recall the instantaneous power is the rate of work, so we have 1 on delta t by the integral of the w dt with respect to time, and therefore this becomes an integral over the work on a change in time. So this integral is the net work done by the gravitational force in this case. So from y equals 0 to y equals h, the gravitational force does negative work because it points against the direction of motion of the ball. So we have minus mgh, and from this point to h on 2, the gravitational force does positive work. So therefore, we end up with the net work as minus mgh on 2. And we can find h using the following kinematic equation. So we have v squared is v0 squared minus 2gh. So the speed at the top of the trajectory is 0. So we end up with h is v0 squared on 2g. And if we substitute for h and divide through by delta t, we get the average power. So the g's will cancel, and we get minus m by v0 squared on 4 delta t. So the correct answer is E. An object is raised using a massless cable and pulley system or a frictionless inclined plane. And what is the benefit of using the inclined plane? So firstly, if we apply a force in both cases, we see that the force is equal to mg in the case of the cable and pulley. So where the block's at equilibrium, we apply Newton's first law. So the force is equal to mg. Now in this second case, we have the force of weight acting downwards and a normal force acting perpendicular to the plane, which is a frictionless plane. So in this case, applying Newton's first law, we have F is equal to mg sine theta. So in both cases, if we add a bit more force, the block will start to accelerate. So in the case of the inclined plane, this force that we need to apply to move the object is smaller, and therefore B is the correct answer. And for your information, for case A, the work required to move the object is reduced, which is not true, because if we want to raise this block a height h, and similarly raise this block to the same height h, then the work done by the force F against the gravitational force is equal to mgh in this case, and the work done by this force against the gravitational force in this case would be mg sine theta by the distance travelled by the block up the plane. So as we can see, sine theta is h on d, and therefore d is h on sine theta. So we still get the same amount of work done to move the block the same height, because the gravitational force is path independent, being a conservative force. And part C is wrong, because in the case of the inclined plane, the block is moved over a longer distance, and in part D, the time required to move the object is not reduced, given that longer distance that the block has to travel, versus straight up to a distance h. A projectile is launched with an initial speed v0, an angle of elevation theta from the horizontal. Find the maximum height reached. So we'll solve this by a conservation of energy rather than using kinematics, where we have a constant gravitational acceleration. So the kinetic energy at point A is 1/2 by the mass by the speed squared. So recall on the projectile motion, the horizontal component of velocity remains constant, so it has a magnitude of v0 cosine theta. So therefore the kinetic energy at B is 1/2 by the mass of the projectile by v0 squared cosine squared theta, and plus the gravitational potential energy at B, if we take our reference point at A. So if we divide through by m, we have 1/2 by v0 squared, and subtracting this term from the right hand side, we have 1 minus cosine squared theta, and that's equal to GH. And solving for h, and using the trig identity, that 1 minus cosine squared theta is sine squared theta. We get v0 squared sine squared theta on 2g. So the correct answer is C. A rock with a mass m is launched from a slingshot. Derive an equation for the potential energy stored in the rubber as a function of x from the graph below, which is the force versus the distance of the rock from the equilibrium position. So recall the force F is the negative of the slope of the potential energy function, where F is a conservative force, and if we multiply through by -1, we get du dx is minus F, which is e to the lambda x minus 1. And then separating the variables and integrating both sides, we get the integral over u is the integral of e to the lambda x minus 1 over x. And because we're getting the potential energy as a function of x, we'll integrate from x equals 0, being the equilibrium point where the force is 0, to x. So therefore we get u on the left hand side is equal to 1 on lambda by e to the lambda x minus x evaluated from 0 to x. So therefore u of x is 1 on lambda e to the lambda x minus x minus 1 on lambda e to the 0 plus 0. So if we factor out 1 on lambda, we get e to the lambda x minus 1 and minus x. So the correct answer is A. A 10 kilo cart, initially at rest, rolls along a frictionless surface from A to B. It then travels along a surface with a kinetic friction coefficient from B to C. And what is the speed at C? So taking our reference point at y equals 0, and taking a conservation of energy from A to C, we have the potential energy at A being the mass by the gravitational acceleration, by the height, noting that the cart's initially at rest, so the kinetic energy at A is 0, and minus the work done by the kinetic friction force from B to C. So that will be the kinetic friction coefficient by the normal force, which is the mass by the gravitational acceleration, and then we multiply the kinetic friction force by 3 meters to get the work done. And that's equal to the kinetic energy at C, which is 1/2 by the mass of the cart by the speed at C squared. And now if we solve this equation for the speed, we get Vc is 13 meters per second. So the correct answer is E. Superman has a mass m on Earth. Derive an equation for his instantaneous power output in terms of the mass, gravitational acceleration, constant k, and time t. So we're equal to the instantaneous power is the rate of work, which is the rate of change of work with respect to time. And by the chain rule, we have the work as a function of y, so we can differentiate it with respect to y, and multiply by dy dt. So this is Superman's force against gravity, and this is his velocity. So dw dy is the slope of the work function, which is mg, and dy dt is 2 kgt on 2, which is kgt. So we can simplify this to kmg squared by t. So the correct answer is B. Now that you've completed the first quiz, let's look at the main topics you should know when revising the work, energy and power unit. So the first thing is the vector dot product. So we have the dot product between a force and a displacement vector is equal to the magnitude of the two vectors by the cosine of the angle between them. So this gives the work done by a force, and know when the dot product is positive, negative, or 0, which will give you the sign of the work done by the force. And where the force is not constant, so it may be a function of position along a curve, then you take the integral of the dot product of the force with the displacement vector. So in one dimension, where the force is non-constant, we can use this integral, and the area under the curve between two positions gives the work done by the force. Now the work energy theorem states that the work done by the forces acting on an object is equal to the change in kinetic energy of the object. And the kinetic energy is 1/2 by the mass by the speed of the object squared. And know the two types of potential energies, being the gravitational potential energy, which is the energy due to the position of an object in a gravitational field, and the elastic potential energy is the energy stored in an elastic object, such as a spring, which has a stiffness of k. And know the difference between conservative forces, such as the gravitational force, where the work done does not depend on the path taken by an object. So for example, if this particle takes the following path to this point, and takes another path to the same point, then the change in gravitational potential energy is the same, as it only depends on the height between the 2 points. So if the particle takes this path and returns to the same position using this path, then the work done by the conservative force over a closed path is 0. And an example of a non-conservative force is friction. So this kinetic friction force will do a different amount of work if the particle travels along this path compared to this path. So therefore the work done by a non-conservative force is not 0 over a closed path. And know how to interpret potential energy diagrams for conservative forces. So remember that a conservative force is the negative of the derivative of the potential energy function with respect to the position of the object that the force is acting on. So from this energy diagram, you should be able to identify the equilibrium points using this relationship. So where the force is 0, or where this derivative is 0, the slope of the tangent at the potential energy function is 0. And these are equilibrium points. And know how to determine whether these points are stable or unstable equilibrium points using this relationship. And for conservative systems, the conservation of mechanical energy states that the total energy of the system is always constant. So here we consider three types of mechanical energy, being the kinetic energy, and the gravitational and elastic potential energy. So if we apply the conservation of mechanical energy to this system, for example, where there's no friction, then the total energy at point A is equal to the total energy at point B or C, or any other point along this plane. And if you had a non-conservative force present, such as a friction force, then the work done by the non-conservative force is equal to the change in the total energy between 2 points. And in some problems, you can apply both the conservation of energy and force analysis, such as in the case of vertical circular motion. You may know the critical speed at this point, and use that to determine the speed of the particle at other points. And know how to identify conservative systems. And in conservative systems, the only external work done on these systems is due to a conservative force. And in the case of the pendulum, being gravity. And know what power is. So the instantaneous power is the rate of change of energy with respect to time, or the rate of work done on an object. And using a bit of calculus, you can derive another relationship where the instantaneous power is the dot product between a force acting on an object and its velocity. And you can also determine the average power from the instantaneous power. And once you've had adequate revision, also using the linked playlist below, you can move on to the next quiz. A 5 kilo block is dragged along a surface and released with a speed of 5 meters per second. And we're asked to calculate the maximum distance traveled by the block. So we can use a conservation of energy. So we have the initial kinetic energy, which is 1/2 by the mass of the block by the square of the speed, minus the work done by the friction force, which is a kinetic friction force. So we have mu k by the mass of the block by the gravitational acceleration by the distance traveled, and that's equal to the final kinetic energy, which is 0. Because when a block reaches a maximum distance, it is at rest. So if we solve this equation, we get the distance traveled being 3.1 meters. So the correct answer is B. If a block slides east with a speed v, how much work is required to reverse the direction of the block so it travels west at the same speed? Well, by the work kinetic energy theorem, the work done is equal to the change in kinetic energy of the block. So we have the final kinetic energy being 1/2 by the mass of the block by the speed squared, minus the initial kinetic energy of the block, which is 1/2 by the mass by the square of the speed. So therefore the net work done is equal to 0, and the correct answer is A. A particle travels a distance s to the right along a curved path. Which integral gives the work done by the kinetic friction force? Well, recall that the work integral is the integral of the dot product of the force and a displacement vector. So in Cartesian coordinates, we can write the friction force vector as minus the magnitude of the friction force, cosine theta, in the horizontal direction, minus the magnitude of the friction force, by sine theta in the vertical direction. And the displacement vector can be written in a similar way. So the magnitude of the displacement vector by cosine theta in the horizontal direction, so that's the component in the x direction, plus the magnitude of the displacement vector by sine theta being its component in the vertical direction. And therefore the work done by the kinetic friction force is equal to the integral of the dot product between the kinetic friction force and the displacement vector. So we have minus ffk cosine theta by ds cosine theta. So we have cosine squared theta multiplied by ds, which will factor out, and minus the magnitude of the kinetic friction force by sine theta by ds sine theta. And cosine squared theta plus sine squared theta is 1 by the trig identity. So the correct answer is C, as the kinetic friction force does work against the motion of the particle. A 1 kilo rock is launched from a slingshot from a position x0 from the equilibrium position. Find the speed of the rock when it reaches x is 10 centimeters. And we have the following potential energy function. So the energy that's input into the system is the potential energy at x0, and that's equal to the kinetic energy plus the elastic potential energy at x. So the potential energy stored in a rubber band at 15 centimeters or 0.15 meters can be obtained by substituting 0.15 into this equation, and using the constant lambda is 30. So that gives 2.817 joules, and the potential energy at 10 centimeters can be obtained in a similar way. So that's 0.536 joules. And then substituting into this expression, we have 2.817 is equal to 1/2 by the mass of the rock by the speed of the rock squared plus the potential energy at 0.1 meters, which is 0.536 joules. And then solving this equation, we get 2.1 meters per second. So the correct answer is A. The potential energy of a particle attached to a nonlinear spring is plotted below. Calculate the equilibrium positions of the particle and state if they are stable. So recall that the force is the negative of the derivative of the potential energy function with respect to x, and at an equilibrium point, this force is equal to 0. So therefore differentiating u with respect to x and multiplying it by -1, we get -1 minus -3 by x minus 2 squared, and that's equal to 0. So if we solve this equation for x, we get x minus 2 squared is equal to 1/3. So the equilibrium points are at x equals 2 plus or minus 1 on root 3. So that will be this point and this point, where the slope of the potential energy function is 0. So at some point to the left of the equilibrium point, the slope of the potential energy function is negative, So from this equation, the force points to the right, and on this side, the slope of the potential energy function is positive. So the force points to the left. So this is a stable equilibrium point because the force is a restoring force. And for this equilibrium point, the slope of the potential energy function on the left is positive. So the force points in a negative x direction. And on this side, the slope is negative. So the force points in a positive direction. So the force acts to pull the particle away from the equilibrium point. And therefore this is a point of unstable equilibrium. So therefore the correct answer is C. A 2 kilo mass is initially at rest and subjected to a variable force given by the following graph. What is the speed of the particle as it travels from x equals 0 to x equals 3 meters? So here we can use the work kinetic energy theorem. And the work done by the force is the area under the force position curve. And the area of a trapezium is the average of the parallel edges, which is 1 plus 3 on 2. So that's x in meters, and multiply by the force, which is the height of the trapezium. So we get Newton meters or joules for units of work. And the initial kinetic energy of the particle is 0 because it's at rest. So therefore the work done is equal to 1/2 by the mass by the speed of the particle squared. So that gives a speed of 4.5 meters per second. So the correct answer is A. A 3 kilo particle rolls up an inclined frictionless plane with an initial velocity of 12 meters per second directed along the plane. Calculate the magnitude of the compression force in the spring given the stiffness of the spring. So the compression force in this spring will be K by D. And using a conservation of energy between points A and C, we have the initial kinetic energy of the particle, which is 1/2 by the mass by the square of the speed. And we'll take the reference potential energy at point A. And here we don't have any non-conservative forces because it's a frictionless plane. So this is equal to the total energy at point C. So when the spring's compressed, the kinetic energy of the particle will be 0, and the elastic potential energy in the spring will be 1/2 by the stiffness of the spring by the compressed distance squared, and plus the potential energy of the particle, which is the mass by the gravitational acceleration by 5 plus d meters, and that's multiplied by sine theta. And if we substitute for the known values given in the problem and rearrange this equation, we obtain the following quadratic. And now we can solve this quadratic. So we get D is minus B, which is 0.075 plus or minus the square root of B squared minus 4 by A by C. And that's all divided by 2A, which gives the following result. So the spring will be compressed in a positive direction when the particle reaches point C. So we take the positive root. And if you multiply this by the stiffness of the spring, we get the force in the spring. So the correct answer is C. A particle with a mass m is undergoing vertical circular motion. What is the speed at d if the particle is travelling at the critical speed at b? So recall at the top of the circle the force of weight and the tension force in a string both provide the centripetal acceleration. So we have Ft plus the mass of the particle by g is equal to the centripetal force, which is mvb squared on r. And when there's no tension in a string, that's the critical speed where the ball is about to fall inside the circle. So we take Ft is 0, and therefore the critical speed is equal to root gr. And now if we do a conservation of energy between points B and D, we have 1/2 by the mass of the particle by the critical speed squared, plus the potential energy. So taking D as our reference point, we have mg by 2r. And that's equal to the kinetic energy at D, which is 1/2 by the mass by the square of the speed at D. So if we multiply through by 2 and divide through by m, we get gr plus 4gr is equal to the speed at D squared, and therefore the speed at point D is the square root of 5gr. So the correct answer is D. A particle slides down a frictionless circular slide, which has a radius of r, starting from rest at a height of 3r above the ground. What is the horizontal distance x from its initial position to the point at which it strikes the surface? So we'll do a conservation of energy between points A and B, where the particle leaves at a horizontal velocity and undergoes parabolic motion as a projectile. So at point A, the particle's at rest, so the kinetic energy is 0, and the potential energy is mg by the height 3r above our reference point of 0. And that's equal to the kinetic energy at B, being 1/2 mv squared, plus the potential energy at B, which is mg by 3r minus r, or 2r. So if we solve this equation, we get the speed of the particle is root 2gr. And using a horizontal projectile motion equation, we have the final x position is the initial x position, being r, plus the horizontal component of velocity by time. And the vertical projectile motion equation gives the final y position is the initial y position of 2r, plus the vertical component of velocity by time, which is 0, minus g by t squared on 2. So that gives the time t being equal to the square root of 4r on g. And substituting for v and t, we get x is equal to r plus the square root of 2 by 4, which is 8, by g on g, which cancel, by r squared. So root r squared is r. And therefore, we get x is 1 plus root 8, which is 2 root 2, by r. So the correct answer is D. A force which is a function of x acts on an object of mass m, which has an initial speed v0 at x equals 0. What is the speed of the object as a function of x? Well, remember our work kinetic energy theorem, where the work of a force in one dimension is the integral of the force with respect to x, and here we integrate from x equals 0 to x. And that's equal to the change in kinetic energy, which is 1/2 by the mass by the speed squared minus the initial kinetic energy, which is 1/2 by m by v naught squared. So evaluating the integral, we have 3x cubed on 3 minus 2x, evaluated from 0 to x, which is equal to x cubed minus 2x. And that's equal to the change in kinetic energy, which is 1/2 m by v squared minus v naught squared. And multiplying through by 2 and dividing through by m, we get v squared minus v naught squared is 2 on m by x cubed minus 2x. And then we can take the initial speed to the other side and take the square root. So that gives v is 2 on m by x cubed minus 2x plus v naught squared to the half. So the correct answer is B.